Hi there, this is exercise 11b, and we're going to look today at integration again, but now using a method called substitution. And it's an important method where you kind of use, it's like the chain really, but a more complicated version, and it can get quite tricky. And in actual fact, you can see it in play up here in this example, where what we've tried to do is we've tried to simplify quite a complicated integration, x cos x squared dx. You can see this is something times something else, and we've made it cos u du, so the letters changed and all sort of things are going on, and even the limits have changed. So notice that goes from 0 to root pi, but now suddenly it goes from 0 to pi, and there's a half suddenly appeared. So there must be something at play here, and I want to talk you through this. Now here's our starter. First of all, integrations, just remind you of this. Hopefully you can do this. You might want to pause this and then see if you can do it. These are 4 examples from our last lesson on exercise 11a. So hopefully you've paused this, and I'm just going to quickly do them now. So that e becomes just 2, you divide it by minus 6, e to the minus 6x plus a constant. Now obviously that can be simplified. Let's see if they all come up together. So this obviously becomes a third, and minus a third at that. This number 2, you've got 1 plus 2x now to the 6. So I need to divide by that 6 plus a constant. That was fairly straightforward. Add a power, divide by the 6. Don't forget though to divide also by the 2. I nearly went wrong. So it becomes 12 on the bottom. That would be a bad mistake. This one becomes the logarithm, the log of the bottom. But then you need to divide by the differential of this, and differentiate that, you get minus 1. So dividing by minus 1 is the same as timesing by minus 1, so minus log of 1 minus x plus a constant. Oh, this one I better tidy up a bit. This is 4 plus 5x to the half. And we did say we can integrate these as long as they are linear functions, and they are. This was linear, this is linear. This is the one where I nearly made a mistake by not dividing by the differential of the bracket last time. So hopefully I'll remember to do it this time. So it's 4 plus 5x. It was to the half, it's now to the 3 over 2. And if I divide by 3 over 2, that's the same as dividing, or times in by 2/3. I suppose it's best to do that. But I also need to put the 5 on the bottom as well, because when I differentiate that, I get 5. So this gives me, I reckon, 2/15. 4 plus 5x to the 3 over 2 plus a constant. And that was the only one really I wanted to check. And luckily I got that 12 in the end. So there are my examples, but now we want to do the integrations, and I've said it's a 4-step process. You want to write these 4 steps down. Number 1, write part of the integral as u equals, sometimes be obvious, sometimes less so. Then differentiate, a bit weird, we're doing integration, but I'm going to have to differentiate to find du by dx. Rearrange du by dx to get dx equals, and then I substitute it back into the integral. And finally I'm going to integrate, or write in the answer in terms of x. There's 4 stages, probably best if I show you this here. So this is the thing I don't like. So I'm going to write u equal to 1 plus x cubed. And when I write that, I can then differentiate it du by dx. Differentiate this gives me, the 1 disappears, gives me 3x squared. And you'll notice what I want to do then, I don't want du over dx, I want dx equals. So these two things effectively switch places. The dx comes up, the 3x squared goes on the bottom, and this becomes du over 3x squared. Now, let's cast our minds back over to here. It said the integral of x squared, which I'm going to keep, but then this became u to the 4, and the dx became du over 3x squared. Du over 3x squared. Now this substitution doesn't work if I've got x squareds and u. I've got to somehow get rid of the original x's. And luckily those x squareds cancels with those x squareds. And now it's the integral of u to the 4 over 3. Notice I haven't done any integration yet. All I've done is differentiation and rearranging. And at this stage then I can, because it says u and du, and there's no x's left, add a power, u to the 15. Divide by that power, and there's a 3 on the bottom already, so that's over 3 5s are 15. Oh, well, that's not very good. U to the 5, add a power, gave me 5. Now, notice in itself this is wrong, because what I need to do is get rid of my u. I need a get back to my x's. My u was 1 plus x cubed. So this is 1 plus x cubed to the power of 5 all over 15 plus a constant. Hopefully my answer says that. 1 plus x cubed to the 5 over 15 plus a constant. Tick. Example 2. So this is what you're getting used to, the fact that you get this double expression. Now sometimes you need to do two substitutions. We are lucky at the moment we're not having to do that. So example number 2, I'm going to write this expression, u equals 1 plus x squared. Now it's probably worth me initially thinking to myself, well, what was this? This is like 1 plus x squared to the half. So I can write u to the half. But before I can write dx, notice I can't leave it as dx because I want to make it substitute into u's. So this is why I have to do this weird thing of differentiation on an integration problem. But if I differentiate the u, the 1 disappears, the x squared becomes 2x. Rearrange again. This gives me dx equals du over 2x. So both of those things go down, the dx goes up. And now I can replace the dx here with a du over 2x. And you'll notice the x goes. And so that's because of that, x goes. Now, that I can do it. And you'll notice also there's a 2 here. So I'm going to write this as a half, and I'll just bring it out to the front. It almost comes out to here. It's on the bottom, so it becomes a half. The integral of u to the half du. What do? You add a power, divide by the power. So it's a half u to the 3 over 2. I've got to divide this by 3 over 2. Plus a constant. Now, you can do it on your calculator if you prefer. It's a half divided by 3 halves. And I was always taught to turn it upside down and multiply, so you can see it becomes a third effectively. So that this is a third of u to the 3 over 2 plus a constant, and I'm still not finished because I've now got to write it as in x's. Now what was u? It was 1 plus x squared. The 3 over 2 plus a constant. Now notice a couple of things here. This all worked because the x is cancelled. The trick allowed us to do this, and notice the reason why it did that was because the power in the bracket was 1 higher than here, so when I differentiated it was the same. So if you see these, they do work. Does that give me the right answer? Yes, it has. So on this one I've got well, it's e to the 3x. Now be careful e's because they aren't the same rule. This rule up here was add a power divided by the power. It's not the same rule as we've seen before. So I suppose my first thoughts is I want to write this as e to the 3x times by 1 plus e to the 3x. And I'm going to get rid of the fraction, as you can see, and make it a negative power. I think that just makes a bit more sense. And if that's the case, I can therefore write u equal to this 1 plus e to the 3x. And therefore I can differentiate that. Now this is differentiation, remember. I'm not integrating, so I'm not going to bring the 3 down to the bottom. I'm differentiating. So when I differentiate, it just becomes 3e to the 3x. Dead easy to integrate that, I reckon. And when I do this, remember, that switches places with that, and I end up with dx equals du over the 3e to the 3x. Okay. So I reckon I'm in a position now where I can probably now write this out. So this becomes the integral of e to the 3x, hasn't changed. This 1 plus e to the 3x is now u to the minus 2, and dx has become du over 3e to the 3x. The great thing about that is they cancel. That's the whole point about doing it. That's what I've been saying. So this is really the integral of a third u to the minus 2 du. So my rule now is add a power and divide by the new power. This becomes, well, it's a third u to the minus 1. Divide by that minus 1 gives me minus a third u to the minus 1 plus a constant. And I think now, only now, am I able to write a third of u to the minus 1, well, u was 1 plus e to the 3x. So the minus 1 plus a constant. Now this could go underneath. Let's say if I've done, yeah, I'd put it underneath in my example on the slide. But other than that, it's the same thing. So this is now integration with logarithms. Now you should remember from before that if we ever integrate, say, 3 over 2x plus 1 dx, we've already seen this kind of example in action where we know it's going to be log of the bottom plus a constant, but it says 3, so I need to put a 3 in the front, and because it's got a 2x plus 1 on the bottom, I have to divide by that as well. Now this rule here is a more general version of that, and it's saying if I integrate a function where the differential of the bottom, if I differentiate the bottom, I get the top. If you ever see one example like this, it basically becomes a log of the bottom still. Now I suppose this is like this, well, kind of like this. If I differentiate the bottom, I get, well, 2. It's kind of like a number, a bit like the top is. So it doesn't have to be exactly the same, and I can still use a rule. So here's a couple of examples. Now, on the face of it, this first one isn't right because it says I've got cos x on the bottom, I've got 3 plus 4 sin x on the cos x on the top, sorry, and 3 plus 4 sin x on the bottom. And I've said I've got to be able to differentiate d dx of the bottom. It should be the top when I differentiate it. And of course, when I differentiate 3, it disappears. And when I differentiate sines, you should remember they're all sine cos minus cos. So if I differentiate sine, I get cos. And it says 4, so the answer to this differentiation is 4 cos x. Now, I actually wanted cos x on the top. It's not the same, but it's close enough to it for me to use this rule. And essentially what I say to myself is if I integrate this, it should say 4 cos x on the top. It doesn't, it says cos, so it's basically too small. So that means I divide by that 4 to make it smaller, and it's a quarter of the log of the bottom, 3 plus 4 sin x. Don't forget your constant. This second one is very similar, I think. Let's just see. Now let's just say to yourself, what do I get if I differentiate that? Well, it's quite a large expression on the bottom. So I'll just write it out so you can see what it is I'm doing. If I differentiate that, and again it's a weird thing that I'm having to differentiate on integration questions, but that's what we have to do. So if I differentiate x cubed, I get 3x squared. If I differentiate 3x squared, I get 6x. If I differentiate minus 21x, I get minus 21, and the 6 disappears. Now, is that the top? And the answer is no, it's not the top. But actually, it's closer than you think. That's times by 3, that's times by 3, that's times by 3. In actual fact, this is 3 times the top. So what this is saying to me is it kind of works, this thing. It does work, but the top's too small by a factor of 3. So my answer is going to be a third of the log of the bottom. And that's all I've got to do. So just look out for this. This comes up so often in a variety of situations, including integrations. A topic called partial fractions, for instance, often appears. So that's right, a third of the log of all of that, and a quarter of the log of that. So that's right. Now this is what we're going to be doing in class. Hopefully you got your head around that, and we are going to be looking at this method of substitution in class. Okay.